Today we are here with the module 1 of the chapter 2, that is electric potential. So let's begin this chapter. So let's begin with electric potential difference. Okay, let's consider a source charge positive Q and a test charge Q0. This test charge we need to move from the point B to the point A. When we are moving this test charge Q0 from the point B to the point A, then we need to work against an electrostatic force of repulsion due to this positive charge. And if that work done is W, then if the work done to move a test charge Q0 from one point to another in electric field is W, then the electric potential difference between these points will be given as this: VA minus VB is equal to W upon Q0. This is the expression for the electric potential difference. Now with the help of this expression, we will define electric potential difference. So watch this. If we take this Q0 as 1, let's take this. If Q0 is equal to 1, then VA minus VB is equal to W. Now we will read this. The work done to move unit charge between 2 points is equal to the electric potential difference. Hence, the work done to move unit charge from one point to another in an electric field is equal to the electric potential difference. It is represented as VA minus VB. Its unit is joules per coulomb or volt. Why joules per coulomb? The unit for the work done is joules and the unit for the charge is coulomb. That's why the unit is joules per coulomb, and this is also called volt. Now some more about electric potential. Watch here. At the point A, when the charge Q0 comes to the point A, then it experiences more electrostatic force of repulsion than at the point B. At point A, it will experience more repulsive force due to this positive charge. Hence, the potential at A will be higher than the potential at B. So we can say that nearer the charge Q0, higher the potential. This test charge will be nearer to the source charge, then the potential will be higher. This point A is nearer to the source charge, that's why the potential at A is higher than the potential at B. And vice versa, far away the charge Q0, lesser the potential. This point B is far away from the source charge positive Q, hence the potential at B is lesser. Or if we take this Q0 very far away, that is at infinity, then the potential will be 0. That is, the charge Q0 at infinity, that is very far, the potential becomes 0. On the basis of this, we will analyze the electric potential. Moving to the electric potential. So let us consider this source charge plus Q and the point A in the electric field, and this test charge Q0 we have taken to the infinity. This test charge is at infinity. We know that the potential at infinity is considered to be 0. Hence, the potential at the point B will be 0. And let us take the potential at the point A as V. So, watch here. When the point B lies at infinity, this point B lies at infinity, then VB becomes 0 and VA we have considered as V. Now we will apply VA minus VB is equal to W upon Q0. This is the formula for electric potential difference. In this formula we will put the values VB is equal to 0 and VA is equal to V. So put the values. VA we have placed as V and VB we have placed as 0. So this becomes V minus 0 is equal to W upon Q0, or we can write it like V is equal to W upon Q0. This is the expression for the electric potential, and with the help of this expression we will define electric potential. So let's move on. This, let us take this Q naught as 1. So if Q naught is equal to 1, then V is equal to W. Now we will read this to make the definition. The work done to bring unit charge from infinity to the point of electric field is equal to the electric potential at that point. Hence, the work done to bring unit test charge from infinity to the point of electric field is equal to the electric potential at that point. It is represented as V. Its unit is joules per coulomb, as that was in electric potential difference, or volt. And one more thing, electric potential is a scalar quantity. We don't need to define the direction of the electric potential, as it does not have any direction. It is a scalar quantity. Now, electric potential due to a point charge. Let us consider the source charge plus Q and the test charge Q naught at the point A, and we need to find out the electric potential due to this due to this plus Q charge, which is a source charge, at a distance r, that is at the point A. This is the point charge due to which we have to find out the electric potential at the point A. So what we need to do, we need to place a test charge Q naught over here, and the electrostatic force between these two charges will be given as. The electrostatic force between plus Q and plus Q naught is F is equal to 1 upon 4 pi epsilon naught Q naught upon R square. Let us take this as equation 1. Now watch here. This charge Q naught we will analyze. We will find out the work done, the small work done to move this charge Q naught by a small distance dr. When we have calculated this small work done, then we can calculate the total work done to bring this charge from infinity to the point of electric field. What we needed to do, we must find the small work done to move this small distance, then we will integrate that to find out the total work done. So let's find out the small work done to move the charge Q naught by a small distance dr, that is from P to A. This will be dw is equal to fdr cos 180. Why this cos 180? Watch here. The direction of F is towards this direction, and the direction of the displacement is in this direction, means the angle between the force and the displacement is 180. That's why we have taken as dw is equal to fdr cos 180. Now put the value of cos 180, which is minus 1. So this becomes dw is equal to minus fdr. Now we will place the value of F from the equation 1. So let's do this. From equation 1, we have placed the value of F, which is 1 upon 4 pi epsilon naught Q naught upon R square. Now, what we need to do to find out the total work done, we have to integrate this expression. So, integrating, we get this. Integrating 0 to W, dW is equal to this 1 upon 4 pi epsilon naught is a constant we have taken as it is. This Q and Q naught are constant, we have taken as it is, and this R is varying. That's why we have taken this within the integration dr over R square. This dr here and this R square in the denominator, and we are integrating from infinity to the R because we are bringing the charge from infinity at the distance R, that is at the point A. Okay, now watch here. That R square in the denominator, when it comes to the numerator, becomes R raised to the power minus 2. Now we can integrate this. What will be the integration? This R raised to the power minus 2, adding 1 in power, dividing by new power. So let's see in the next term. Watch here. The integration of this dw becomes w, and the limits, lower limit 0 and the upper limit w, is equal to minus 1 upon 4 pi epsilon naught as it is, Q naught as it is, and this R raised to the power minus 2, adding 1 in power, dividing by new power. Now we will solve these powers. Minus 2 plus 1 becomes minus 1, and also this minus 2 plus 1 becomes minus 1. So this R raised to the power minus 1 upon minus 1. This minus 1 will be multiplied to that minus and will become positive. So watch here, this becomes positive 1 upon 4 pi epsilon naught q naught as it is, and this r raised to the power minus 1 we have written as 1 upon r, and the limits, lower limit infinity and the upper limit as r. Now we will place the limits. Watch here, in the place of w we will place the upper limit minus lower limit. In here, in the place of r we will place the upper limit minus lower limit. So watch here, upper limit w minus lower limit 0 is equal to 1 upon 4 pi epsilon naught q naught. In the place of 1 upon r, the value of r we will take as r in case of upper limit, so this will be 1 upon r minus, in place of r we will put the value infinity, so this becomes 1 upon infinity. Now this 1 upon infinity equals to 0, so in the next term w minus 0 becomes w, this as it is 1 upon r as it is, minus 1 upon infinity becomes 0. Now this expression can be written as w is equal to 1 upon 4 pi epsilon naught q naught upon r. This is the expression of the work done when we bring a test charge from infinity to the point of electric field. Now we need to find out the electric potential due to the point charge. So let's place the formula. The formula for electric potential is, V is equal to W upon Q naught. Put the value of W that we have calculated, that is this 1 upon Q naught as it is, and the value of W is 1 upon 4 pi epsilon naught Q naught upon R. This Q naught will be cancelled out by that Q naught, and we will get the expression 1 upon 4 pi epsilon naught Q upon R. This is the expression for the electric potential due to a point charge. Now let's move on to the electric potential due to a dipole. We have discussed about the dipole in the previous chapter, and we have calculated the electric field due to a dipole in axial and equatorial position. In the same way, we will calculate the electric potential due to a dipole in axial position and in equatorial position. So let's calculate the electric potential due to a dipole in axial position. Let us consider an electric dipole of the charges minus q and plus q separated by a distance 2a. This a and this a sums up to give 2a, and we need to find out the electric potential at the point P. For that, we have to find out the electric potential due to this negative q charge at the point P, and we have to find out the electric potential due to this positive q charge at the point P. Then we will calculate the net electric potential at the point P, which will be the electric potential due to the dipole in axial position. So let's calculate. First of all, the electric potential at P due to the charge minus q, due to this charge minus q. As we have the formula for electric potential 1 upon 4 pi epsilon naught q upon r. R is the distance between the charge and the point of observation. Here the charge is minus q and the point of observation is P. Then the distance between them will be a plus r or r plus a, and this charge is negative q, that's why we have taken this as negative q. In case of electric field, we were not taking this sign. Why? Because we have already defined the direction in the case of electric field, but in case of electric potential we will not be defining the direction because it is a scalar quantity. So in case of a scalar quantity, we cannot define the direction. As we haven't defined the direction, that we will calculate with the sign. We will take the sign in this because we cannot define the direction because it is a scalar quantity. So this is the electric potential due to the charge minus q. Now the electric potential at P due to the charge plus q will be 1 upon 4 pi epsilon naught plus q upon the distance between the charge plus q and the point P will be r minus a. So this we have taken as r minus a. Now we need to calculate the net electric potential at P, which will be given as the algebraic sum of both these potentials, that is V1 plus V2. Now put the values of V1 plus V2. The value of V1 we have taken, that we have determined, is 1 upon 4 pi epsilon naught minus q upon r plus a, and the value of V2 is 1 upon 4 pi epsilon naught plus q upon r minus a. let us take this 1 upon 4 pi epsilon naught as common. Then we will get this, and we have taken this q also as common. Then this becomes minus 1 as it is here, this becomes plus 1 as it is here, this r plus a comes here, and this r minus a comes here. Now we will solve this, and we will get like this expression. This r plus a and r minus a multiply together, this r minus a multiply with minus 1 becomes this r plus a multiply with plus 1 becomes this. Now further we will enter this minus 1 into the bracket, so this becomes minus r plus a plus r plus a, and in the denominator this becomes r square minus a square. This minus r cancel out by that r, and this a sums up to give 2a. Then we will get q upon 4 pi epsilon naught, this becomes 2a, and this r square minus a square as it is here. Now this q and this 2a, this q into 2a becomes p, that is electric dipole moment. This q into 2a we can write it like p, which is electric dipole moment. This is the expression for the electric potential due to a dipole in axial position. Alright, now we will elaborate this expression for the electric potential a little bit more. Watch here. If we are taking a is very less than r, then we can neglect a. If a is very less than r, then we can neglect this a. We can neglect this a. Then we will get 1 upon 4 pi epsilon naught p upon r square. This is the final expression for the electric potential due to a dipole in axial position. Now moving on with the electric potential due to a dipole in equatorial position. So let us consider a dipole of charges minus q and plus q separated by a distance 2a, this a and this a, and we need to calculate the electric potential at a point p, which is at a distance r from the center of this dipole. So what we need to do, we need to find out the electric potential due to this negative charge at this point p, due to this positive charge at this point p. Then we need to calculate the net of these electric potentials. So let's meet them and find out this distance. This distance with the help of Pythagoras theorem will be under root r square plus a square. In the same way this will be under root r square plus a square. Now find out, due to this charge minus q, the potential at p. This will be the electric potential at p due to the charge minus q will be 1 upon 4 pi epsilon naught charge minus q upon distance which is under root r square plus a square. This we have taken. Let us consider this as equation 1. Now the electric potential at p due to the charge plus q, this one at this point, this will be v2 is equal to 1 upon 4 pi epsilon naught plus q, this charge, and the distance under root r square plus a square. This we have taken as equation 2. Now we need to calculate the net electric potential at p, that will be given as v equatorial is equal to v1 plus v2. Put the value of v1, that is 1 upon 4 pi epsilon naught minus q upon under root r square plus a square, and the value of v2, which is 1 upon 4 pi epsilon naught plus q upon under root r square plus a square. This minus sign take over here, so this becomes minus 1 upon 4 pi epsilon naught q upon under root r square plus a square, and this is 1 upon 4 pi epsilon naught q upon under root r square plus a square. You can see these two terms are identical but opposite in sign. So the resultant of these two terms, when we will add them up, that will be 0. So the electric potential due to a dipole in equatorial position is 0. Moving on to the electric potential due to a system of charges. Watch here. Let us consider a system of charges q1, q2, q3, q4 and q5, which are separated from a point P by a distance r1, r2, r3, r4 and r5 respectively. These are the distances for these individual charges. So the electric potential for the system of the charges will be the algebraic sum of all these potentials, the algebraic sum of the potentials due to these charges. So the net electric potential will be V is equal to V1 plus V2 plus V3 plus V4 plus 5 V5. And if there are more charges than 5 charges, then we will add them up. All right, now put the values. The value of V1 we have taken 1 upon 4 pi epsilon naught Q1 upon R1 because the charge is Q1 and the distance is R1. In the same way, these values 1 upon 4 pi epsilon naught Q2 upon R2 plus 1 upon 4 pi epsilon naught Q3 upon R3 plus 1 upon 4 pi epsilon naught Q4 upon R4 and 1 upon 4 pi epsilon naught Q5 upon R5. We can take this 1 upon 4 pi epsilon naught from each term as common. So watch here, we have taken this 1 upon 4 pi epsilon naught as common and rest of the terms are inside. And we can also write it like this: 1 upon 4 pi epsilon naught as it is, summation I is equal to 1 to 5 because we are adding them from 1, 2, 3, 4, 5, from 1 to 5. That's why we have taken I is equal to 1 to 5 summation Qi upon Ri. When we will expand this, we will put the value of I one by one from 1 to 5 and we will get this expression. This is the summation expression for the electric potential due to a system of charges. Now moving on to the relation between electric field and potential. Watch here, this is the source charge and this is the test charge. This test charge we are moving from the point P to the point A, that is the direction of the displacement, and it will experience a repulsive force in the opposite direction. So the direction of the displacement and the direction of the force are different or 180 degree. So the work done will be given as FDR cos 180 because the angle between F and DR is 180. Now put the value of 180, which is minus 1, so this becomes dW is equal to minus FDR. Now we will place the value of F. This, since F is equal to EQ naught, this is the value of electrostatic force with the help of the definition of electric field. So put the value of F as EQ naught. Now take this Q naught to that side in the denominator of this, so this becomes dW upon Q naught, and this dW upon Q naught we can take as dV. This is from the definition of electric potential. Electric potential is given as the work done upon charge. So the small work done upon charge is equal to the small potential. So this will be dV is equal to minus EDR. This dW upon Q naught we have taken as dV because of this. Now this dV is equal to minus EDR. Let's take this dr to the denominator, then this becomes dV over dr is equal to minus E, or we can write it like E is equal to minus dV over dr. This is the relation between electric field and potential. Moving further with electric potential surfaces. Equipotential surfaces. What are equipotential surfaces? Let's discuss. Watch here. You can see here a charge positive Q. Around this charge there are some spheres. Okay, on the outermost sphere, which is of radius r, we have taken 2 points, the point A and the point B. For these 2 points the electric potential will be this: V is equal to 1 upon 4 pi epsilon naught Q upon R. This 1 upon 4 pi epsilon naught is a constant, this Q is the charge which is constant, and this R can vary for the different surfaces. This surface R is different, for this surface R is different, and for other surfaces the R is different, but V depends on this radius of the sphere. Alright, if we take only a single sphere, this sphere, the surface of this sphere, and we take any point on this surface like point B, point A, or any other point, the radius for any point on this surface will be equal for all the points. So when the radius is equal for all the points on this surface, then this is also constant, and hereby the electric potential will be constant. Means the electric potential at each point of this surface is equal or same. So this surface will be called as equipotential surface, a surface on which the potential is equal at each point is called equipotential surface. So on this surface at each point the potential is same, hereby we can call this an equipotential surface. That is, a surface that has same electric potential at each point of it is called an electric potential surface. So this equipotential surface is nothing but the surface this which has equal potential at each point of the surface, and also at each point of the circle of the radius r the electric potential is same. So v is equal to constant, or we can say dv is equal to 0. Since v is same or constant, whenever we differentiate the constant we get 0. It means differentiation of potential is 0. And when dv is equal to 0, with the help of this formula, E is equal to minus dv over dr, put the value of dv, that is 0, and we will get E is equal to 0. Hereby we can say that the electric field is 0 at each point of the equipotential surface. So that's all for now. See you again in the next lecture. Thank you for now.